Okay, lecture 5, moments on rigid bodies. So today we are going to be working on rigid bodies, kind of defining a rigid body. I think I talked about this a little bit in one of the past lectures, but I'm going to go ahead and bring it up again. And then I'll talk about the principle of transmissibility and moments. And moments is kind of the next key thing that we're working on in this class. In fact, it is really, really, really important. It's as important as forces. And then we're going to define and calculate the moment with a right-handed coordinate system. Having a right-handed versus a left-handed coordinate system is just going to determine the sign of your moment, and it's really, really important that we make sure that we, that we're consistent here. So we're going to use a right-handed coordinate system, and I recommend that you stick with that for pretty much forever, just because that's what people are going to understand. Okay, so I'm going to start with the rigid body and the principle of transmissibility. And these two things, as well as the idea of an internal versus an external force, which your book kind of talks about a lot, they all kind of play into each other. So let's start here by, I'm going to draw a car. All right, so, we got some car. It's a poor drawing of a car, but whatever. Okay, and so if you have some problem and you say to yourself, okay, what's going on with this car? I want to know what this car is. So you break up the system and you say, all right, I'm going to do a free body diagram of this car. Okay, so you're just going to draw, here's my car, right? So your free body diagram doesn't have to be beautiful, and mine certainly isn't. Okay, so in the diagram, a lot of times there'll be things like you'll have the road on there, and maybe you want to know something about, maybe the wind is going around the car, et cetera, et cetera. And when you draw the free body diagram, okay, so instead of having all that other stuff, and you might even have like a force arrow here or a velocity vector telling you which way the car is going, but when you draw the free body diagram, you don't have all of that stuff, right? You think about, oh, okay, well, there's a weight of the car, okay, and that's going to be happening here at the center of gravity, okay, or the center of mass, or whatever you want to call it. And then right here and right here where the rubber hits the road, right, there's going to be kind of a normal force. So there's two of those, and maybe I'll call this force normal front and force normal rear, okay? And then you've got some other forces. So you've got like the road is pushing the car forward. That's why it goes forward. So you've got maybe the force of friction on the front tire and the force of friction on the rear tire, okay? And then you've got air resistance, which is acting somewhere on the front, right? So you've got a force of wind resistance, force of wind. Okay, so now we've drawn all of these forces on there. And so I'm going to start here with external and internal. So the question at this point is, you might say, well, what about, I don't know, the force of the gears in the engine? Or what about the, what about like I'm in the car and I'm kicking the car or something along those lines. Like I'm pushing against the floor, or I'm inside the car and I've got a balloon and it's a helium balloon, and so it has a buoyancy, and so it's like pulling the car upwards. Okay, and so the key here is this: we have to define what our system is. Okay, and if this is our system, and everything within this thing is our system. Okay, and once we do that, then like the free body diagram only has the external forces. It only has the things on the outside of this thing, and everything that's interior to it, we don't care about. Okay, I don't care about anything else that's going inside of the car. All of these things that are happening on that surface, okay, these are all my surface forces. 1, 2, 3, 4, 5, because all of those are happening on the edge of this car. These are surface forces. If it's inside that surface, I don't care about it. If it's outside that surface, I don't care about it, okay? It's only the things that are acting on that surface, okay? The only other force that we care about is this weight, and that is what we call a body force. Okay, now, that said, so we care about the external forces. The internal forces, they're just a part of the system, okay? So we're not going to worry about those, okay? And there's 1,000 different ways that this will simplify your life as long as you correctly draw these free body diagrams. Okay, now once you've kind of identified that and you've thought about that, there's a few like kind of fancy things that we can do, and this is the principle of transmissibility. And so if I look at my free body diagram, okay, and I'm going to draw this car again, and again it's going to be a sloppy drawing, okay, because, whatever. And what this says basically is I can pick up one of these forces, and I'm not going to be able to just grab one on my screen, so I'm going to have to redraw it. But I can pick up one of these forces. Let's say I want to pick up this force right here. Okay, and I can move it wherever I want along that line of action. So if it was acting right here, okay, I could put it right here on my car. And I could call that the force of normal friction, and I could just basically move it from where it's actually acting to somewhere else. And it's okay. Okay, and this is the principle of transmissibility. And I can do that with any of these. So I can take this normal force in the rear, and I can carry it all the way up to the surface if I wanted to. Okay, I could. I could also take it if I wanted to, and I could take it from, I'm not going to be able to isolate it, but I could say, you know what, I don't want it right there. Okay, I'm going to take it down here. I'm just going to take it, and I'm going to go down here. Okay, and even more than that, I'm going to just put it way down here off of the frame if I wanted to. Okay, as long as it is in the line of action of the original force, this is all acceptable. Okay, I can do it with the weight. If I don't want the weight to act here, I can have the weight act here, or I could have the weight act here. Okay, you can do whatever you want. Okay, so my frictions on the wheels, I could have them both act off the front wheel. I could be like, well, I'm going to have this be FFR plus FF, that's rear, so front. Okay, so I could add both of my frictions in the front, okay, if I felt like doing that. Now, there's a thought that should come to your mind when I'm doing this. Like, let's just do the last force here, and let's just take the force of wind resistance and let's put it on the back of the car. Okay, so there's a thought that should occur to you as I'm moving all these forces along their line of action. Okay, so the line of action would be, basically, if you just move the force, in the straight line along itself. Okay, and so. And I'm gonna show this on a simpler free body diagram, but imagine I've got a block, okay, and it's at equilibrium. There's no gravity because I don't feel like dealing with up and down right now as I draw it. But let's imagine I've got a force in this direction, F, and I've got a force in this direction, P, okay, and they're equal and opposite, okay? So I don't know why I chose P. It doesn't matter. So these forces are equal and opposite, so this sucker is at equilibrium, right? But I can conceivably, if I wanted to, okay, according to the principle of transmissibility, and assuming this thing is rigid, okay, I could put F here, and I could put P here, F and P. Okay, and you're like, okay, well, that's fine. Or what if I wanted to go this way, and I wanted to put P here and F here? Okay, they're equal and opposite. So in all three of these cases, the sum of the forces in the x direction equals 0. So we can say that these are all equivalent systems. Okay, equivalent. Equivalent. But some part of you may be looking at this and saying, wait, but that's not equivalent at all, right? Because what's going to happen here is, like in this first experiment, this thing might rip apart in the middle, right? Or it might stretch, okay? Whereas in this middle thing, the forces are acting in the same spots. They're just going to cancel each other out, and this box isn't even going to feel anything. Okay, and in this bottom one, they're going to smush the box like this. Okay, so the key here becomes the fact that, so if the box could be smushed, or if the box could split, or something along those lines, then this would not hold. However, we're going to use the idea that this box is rigid. And so rigid in this case means that it does not deform. So that's kind of the, that's the way your textbook would define it. Okay, and then the principle of transmissibility obviously only applies in that case, because otherwise if things can smush, then this case and this case and this case are not equivalent. Okay, so the principle of transmissibility, so we have the principle of transmissibility, which says that the equilibrium, or lack thereof, of a rigid body is unaffected by, that's the that's the official definition, by replacing a force with an equal force acting at a different point on the same line of action. Okay, and so this equal force actually, of course, has to be acting in the same direction. Okay, so we can move forces around along their lines of action in order to make our lives easier. And that's a key thing that we're going to do, especially when finding moments, because it's just going to make our lives easier, okay? And, you know, we don't really know what a moment is just yet, but we're going to talk about that very shortly. So if we go over here and we're going to think about this, and this is kind of a standard way for people to begin this. This is the way that this was presented to me initially, okay? So, you know, and we're going to start with, you know, some object, and I'm just going to use a standard block floating through space. And we want to ask if it's in equilibrium, if I've got a force here and I've got a force here, and, you know, say this one's 5 pounds and this one's 5 pounds, okay? So we got 5 pounds acting up on one side, 5 pounds acting down on the other side. And the question is this at equilibrium, okay? And we often, or we could, you know, the way we would do this based on last chapter is say, okay, some of the forces in the x, do they equal 0? Okay, and yes, they do. Okay, that checks out, and the reason we know that is because there are no forces in the x direction. So, okay, well, what about the sum of the forces in the y direction? Do they equal 0? And it would say yes. Okay, but why isn't this thing at equilibrium? And it's pretty straightforward to see why it's not at equilibrium. If you were to let this thing go, well, it would spin. Okay, and so basically this one is going to cause it to spin this way, and this force is going to cause it to move in the same direction. So they're both going to cause it to spin in the same direction, so it's just going to spin. It's going to be like your little fidget spinner or, you know, whatever. So what needs to happen, basically, is the tendency for this thing to spin due to those forces need to also add up to 0. So I would say, in this case, the sum of the moments need to be equal to 0. Okay, and that could be around a point, so it could be any point. Usually books use like the sum of moments around 0.0. I don't really know why it's always 0.0. For me, usually, in this case, I'm going to say the sum of the moments around the z-axis, okay? And so what is a moment? The moment is the moment of a force, okay? So the moment of a force, you won't always hear they say the moment of a force, but is the tendency of that force to cause rotation. Okay, and so, but there's this curious thing, which is these axes, okay? So I've summed the forces in the x, the forces in the y, and the moments in the z, okay? So this is for a 2D problem, okay? And so this becomes a point where we need to start thinking critically about our right-handed rule, okay? So I'm gonna just draw a coordinate system, and here is my x coordinate, and here is my y, okay? And that leaves z to be vertical in this case. Now the question is z up or is z down? Okay, and we'll come back to that in 1 second. But what I want to think about here is, in this case, like over here, where I said some of the moments about z. What I mean is that in this, if this object, for example, if it was, say, this object that I drew here, and I drew it in the x, y, z plane here, okay, so it's kind of got like a shape like this, okay, so it's got a shape like that, okay, and it's totally, completely flat. It has no expression in the z direction. It's an impossible object, right? But whatever, right? This is math class and we're learning, or this is physics and we're learning stuff. Okay, so we've got a 5 Newton acting here. And we, not Newton, pound, excuse me. Let's undo that. Okay, so we've got 5 pounds acting here, and I've got another 5 pounds acting this way. Okay, so those two are going to cause it to want it to spin, okay, and they're going to want it to spin around, you know, in what direction? Not in the x direction, not in the y direction, but look, they're going to spin around this axis right here. Can you see how they're kind of going around? Can you mentally imagine how they're going around that axis? So really, that axis is the only way that I can define its motion, okay? Now the trick becomes, well, what's positive motion and what's negative motion? Which way is that spinning? Okay, so this is where the right-hand rule comes in. Okay, so I'm going to write this over here, right-hand rule, okay? So first I'm going to do this for the coordinate system. Okay, so for the coordinate system, okay, x is your fingers, Although some people will just use the index finger. Okay, Y is your palm. Okay, so you can see, I want you should probably be trying to do this in your own space right now, to point X with your fingers and Y with your palm, and that tells you which way Z is. Z is in the direction of your thumb. Okay, so that's key. Okay, so if you do that, then that determines which way this Z had to be. I could not have, if I had written the Z down here, I'd have been in a left-handed coordinate system. We don't want to be in a left-handed coordinate system. We want to be in a right-hand coordinate system, because everybody in the universe uses the right-hand coordinate system. Okay, and that way, this will hopefully make sense to you. All right, so once you have done that, one of the things to note is that if I think about my fingers, so if I get my fingers lined up with X, or maybe just my index finger, I get my palm lined up with Y, and then I get my thumb lined up with Z. So now I'm in this coordinate system. And now I think about, well, which way are my fingers curling? Okay, and if you're using your right hand, your fingers will curl in this direction, okay? Counterclockwise, essentially, in the XY plane. Okay? So that will tell you that right now, this particular moment, as I have it drawn, of these 5-pound forces, is going the opposite of the way your fingers are going. So the way your fingers are going, so counterclockwise is the way your fingers are going. So that is positive. And clockwise, the way this moment from these two forces is going, that is negative. Okay, and it's always going to be like that. So if I go back to my original drawing, okay, if I go up to here, I can imagine, well, here's my x-axis, here's my y-axis. Okay, and so if I put my fingers in the X direction, my palm in the Y direction, and then I curl my fingers are going to go in the counterclockwise method. So that is the positive direction. So a lot of times what you'll see is before people do this expression right here, what they'll write in front of it is they'll write a little circle like this with a positive sign, and that just reminds them that counterclockwise is positive. Okay? All right, so, okay, that said, okay, well, what is a moment, and how do we get at it? How do we know how much the force wants things to spin? Okay, and so, I'm going to describe it to you real quick, and just kind of like a throwback to my childhood, when I would be in a room and my brother wanted to come in the room, and I didn't want to come into his room. I didn't want him to come into the room. So from above, the door getting into my room might look like this. Okay, so from above. So there's a hinge down here. That's a hinge. And my brother and I would be pushing on the door, right? My brother's 2 years older than me, so he's stronger than me. So he might be pushing, right here. So this is my brother, okay, and this is me. Okay, my brother's stronger than I am, okay? I'm weaker than he is. But who's going to win? Well, in this case, I'm smarter than he is. Okay, because what we're both trying to do, he's trying to he's trying to come into that, he's trying to open that door, and I'm trying to close that door. So he's going, what direction is this? That is clockwise. So he's exerting a negative moment on this door. I'm exerting a positive moment on this door, right? But I have an advantage, right? I'm further away from this hinge, okay? And if you can't picture that, imagine if my brother pushed right here. Well, let's make this an extreme case. My brother pushes right next to the hinge, and I push way out here, okay? I don't have to be anywhere near as strong as my brother if he pushes right next to the hinge. So I have a major advantage. So one thing that affects the strength of your moment is the distance you are away from the hinge, okay, or the thing that you're going to take the moment about, okay? And in fact, if my brother pushed directly on the hinge, he would have no effect whatsoever on turning the door. He would just be wasting his energy, okay? So we could probably say that it's directly proportional to how far away you are. The other thing that's going to be in effect is obviously how strong you are. In this case, my brother's potential moment is much higher than mine. If he goes out here and he pushes here, and I push where I'm pushing, well, he's stronger than I am. I'm not going to be able to win that, right? Because he's just stronger than I am. So these are the two things that really matter. And there's a last little bit too, which is the direction at which you push. So imagine, another thing that would be great is if my brother were not very smart and he pushed on an angle like this. Okay, you can imagine that would weaken his effectiveness, right? Because, and here we'll do a little bit of statics, but because some of his force would be going downwards, okay, or I'm going to put it right here, okay, and that would be creating a moment, but some of his force would be going this way, okay, and it would be doing nothing, because that portion of the force is going to be going straight through the hinge, okay, and so that's important, okay, and so basically a few things matter, okay. We could say that the angle of the force matters, okay, the location of the force, okay, and then the magnitude of the force. These are the things that matter the most. Okay, so let's do okay. So let's go ahead and define this, and then we'll talk about how to calculate it. But these are the things that are going to determine your moment. And you don't have to write that down, but I want you to have a mental image of what's going to create a larger moment, smaller moment, et cetera, because we're going to calculate these for the rest of the semester. It's going to be important to get them. So I'm going to give you a few different ways to calculate them, and we're going to talk about what each one of them is. Okay, so let's begin. All right, so first thing to note of all three of these different ways to calculate this is that moment has a little arrow on top of it. So that little arrow indicates that it is a vector. As I kind of defined earlier when I said that you needed to, what does it mean it's in the z direction? And I don't know why this won't let me draw. Okay, what does it mean that it's in the z direction? Okay, so that's important. So the fact that it has a little arrow tells you that it is, that it is a direction. And then there's really some really great. Oh, what happened here? Oh, everything got moved. Okay, I was like, man, I just drew this on top of other stuff. Okay, anyway, and then we have these three ways to do it, and this one right here is a cross product. Okay, so this is a cross product, so this would be written as R cross F, or what you might sometimes hear this called, you might hear it called a vector product. Okay, these are very common ways to refer to this. And sometimes, just maybe, you might hear this called an outer product. Okay, and that's we're not going to get into that because we're not going to do this in matrix. Well, we're going to do some things in matrix form, but don't worry about that so much. For this class, I'm going to typically call it a cross product. Your book calls it a vector product. So I'm going to try to use vector product more often, but R cross F. Okay, and we'll talk about what R is in a second. Note that in this case, so another way to do this is you're going to multiply, and I think actually this would be the magnitude of this. So the magnitude of M, you could find from just taking the force and multiplying it times a distance, basically a perpendicular distance. And in this case, we're going to go ahead and say this is the magnitude of these two. Okay, and I'll kind of show you how to work that one. And then this last one is that, it falls out of the math of the second one. And that is basically F, the magnitude of F times the magnitude of R times the sine of the angle. And this angle is between F and R, okay? So that's important. Okay, so this is kind of a lot. And what I'm going to say right off the bat is, I won't say it off the bat. We'll kind of get into that. But I'm just going to kind of draw you a thing, and we'll start calculating the moment, and we'll talk about, the advantages and disadvantages of each of these three ways to do this. Okay, so give me a second. I'm going to draw this sucker. All right, so here's a problem. There's some kind of frame here. Maybe to make it a little clearer, maybe I'll kind of color it in a little bit. And it's attached to some sort of, wall or something. Okay, and this frame has dimensions of 0.8 meters tall and 0.6 meters wide. And there's a force acting on the end of it, and the force is acting at 90 newtons. Okay, now it's acting at an angle off of that end. The angle is defined as theta, and we don't really know a whole lot about theta. It can change, although in the first bit it's going to be 15 degrees. And it's attached to this top thing at a point 0, okay, or O, or whatever they want to call it. I think it's usually an O. I actually never know if it's an O or a 0. I guess it's an O. Anyway, I stole this one off the internet. This is probably on somebody's test or in somebody's textbook or something. Anyway, so the idea here is, calculate the moment from F. Like, what is the moment that F is causing? And so what we're going to do is, this is going to be a teaching problem. So I'm going to work figuring this moment out from each of these different methods. And hopefully you'll start to see kind of what they are and how they work. And so the first thing I'm going to do is I'm going to do a vector product. I'm going to talk about what R is, and we'll work from there. So, the answer to this problem is not critical. What is critical is that we kind of understand what these things are. Okay, so we're going to start with this, this thing R. Okay, R. Okay, R is the, it is the position vector. That's kind of usually the way it's described. And really it's going from, okay, so I'm going to draw it and I'm going to describe what this means. Okay, so this is the point we want the moment around. Okay, the point we want the moment around. And this thing is happening anywhere, it's going to go to anywhere on the line of action of the force. Okay? And it always has to be in that, it has to go in that direction. Okay? It's very, very, very important that it goes in that direction. Okay, so that said, I'm going to go ahead and solve for the moment using, we'll call this method 1, method 2, and we'll look into method 3, although I don't really like method 3. I'll look at method 3 real quick and I'll kind of explain it, but as you get further along, this right here, this thing right, this method 3, is something that when people learn cross products and dot products, usually what happens is they're like, oh, okay, the cross product is a sine and the dot product is a cosine, but they can't picture why one is a sine and one is a cosine. And so they just kind of forget which is which. This is certainly what happened to me when I learned it. And so I could never remember which one was sine and which one's cosine. And then all of a sudden, as the years went by and I started looking at it, I'm like, oh, it's a cross product. That's why it's a sine. And so briefly, when we get over to this, we'll talk about how to use method 3 and basically never to use method 3. I don't know. We'll talk about it. And then we'll, maybe there's a time to use method 3. I don't know. But right now I want to use method 1 for this particular problem. And so I want to say the moment of 0 at 0, okay, and this is being created by that force, so it's going to be R cross F. Okay, so if we're going to cross those, then I need to define them. Okay, so M, okay, R. Okay, R is going to start at, let's do this in red. So it's going to start here, and it can go anywhere along the line of action of this force. So it can go anywhere along here. Anywhere, it can end anywhere, any point along that line. Now, unfortunately, no points on that line are very well defined. So what I'm going to do, I'm going to pull out my straight edge, which in this case is my, my driver's license, which, by the way, I highly recommend you use if that's what you need. Okay, and it looks like this. Okay, I'm going to go right to that point because that seems to be the easiest point for me. So that's my R vector. Okay, so I'm going to define that in, since we're in 2 dimensions, I'm going to define that in I's and J's. Okay, so I'm going to get back to white. So I'm going to have an I, and I'm going to have a J. Okay, that's going to be my R. And I'm going to cross it with F. Okay, so in this case, it's going to go in the I direction. It's going to go like this. Okay, 0.6 meters. 0.6 meters in the I. And then the J direction is going to be negative, so that's the Y direction. And so it's going to go down 0.8. 0.8 meters. Okay, boom. All right, so that's my R. Okay, it's my position vector. I could have put this to other points on the line of action if I wanted to. Okay, that would have been difficult, but I could have done it. Okay, so in this case it would have been difficult. There's other problems where it makes a lot of sense to do it in that way, but we're going to leave it like that. Okay, now we're going to cross it with the force vector. Okay, now notice the force vector. Okay, in the the Y direction it's vertical, it's positive, and the X direction is negative. Okay, so we're going to go ahead and see. So I know it's 90 newtons, but this side right here, this vertical side, is going to be 90 newtons times the cosine of that angle. Okay, and the horizontal side, which I'm going to draw over here, this is going to be 90 newtons times the sine of that angle. Okay, so I'll plug those into the calculator for 15 degrees so that we can, well, you don't have to watch me do that. So I'll pause it for a second and I'll just do that. Okay, so we get these, fancy numbers, and again, I always keep 5 significant digits. So negative 23.294 newtons in the I and 86.933 newtons in the J. Okay, so now we have to actually do the cross product. Okay, and the way that we do this, usually we use something called like the determinant. We use the determinant, and there's easier and harder ways to do the determinant. I'm going to recommend, I think it's called Cramer's rule. There's other ways, but let's kind of set up what this is. So this is going to be like this, about 0.0 or O. And so the determinant is typically drawn with some brackets. So we're going to go I, J, and K. Okay. And then since R is the first thing that we're working with, we normally do IJK. Yeah, let's do IJK. So 0.6 meters, 0.8 meters. Okay, 0 in the K. Okay, negative 23. Oh, this is a negative, excuse me. 0.294 newtons and 86.933 newtons and a 0. Okay. Now, some part of you might be going, well, why did we bother with the K here? In fact, my brain immediately flipped and said, we don't need a K because we're only in 2 dimensions. We are in 2 dimensions, but the vector, the moment is going to end up being in the Z direction. It's the only direction the moments can happen when you're in the XY plane. So, all right. So what we do is we need to find the moments, the determinant of this matrix. Okay, now there's a few different ways to do this. Some of you may remember a way where you kind of like follow this out this way. You do IJ like this and 0.6 and negative 23.294 and negative 0.8 and 86.933. And then you do something where you, I'll draw some like dotted lines to kind of give you the idea. Well, I'll just draw them. And you do things where you go like this and like, it's very hard to draw this. Okay, so the first one went through here, and then through here, and then you come back this way, right? Okay, and you basically multiply all the lines going down and to the right, and then you subtract all the lines going down and to the left. Okay, and so that is a way to do this. That's not the way that I prefer. I'm going to look the name of that up if you want to learn how to do it that way, but I'm going to use what we call Cramer's rule because I just think that that's easier. So let's undo these. All right, so the way that we do this Cramer's rule business, I don't know what the way that I just showed you. I don't know what it's called, but if you really want to do it that way, just Google how to calculate a determinant of a 3x3 matrix, and it'll pop right up. But I don't particularly like that method, so I'm not going to use it. So what you do with Cramer's rule, and let me get where we have a little bit of space. So maybe right in here, is we're going to ignore all that green business. Okay, we don't care about the. I don't know why it has a tendency to jump on me. Okay, so we're going to ignore all this green business. Okay, so pretend that that's not there. Okay, so I'm kind of highlighting it so you can still see it if you want to see it, but that's not what we're working on. Okay, so what we're going to do is I'm going to cover one. So I'm going to so we're just going to step up here and I'm going to quote unquote cover the eye. Okay, so now I've covered the eye. And when I cover the eye, that means that this bit remains. Okay, this bit right here. Okay, and I'm going to calculate essentially the determinant of that. So what I'm going to do is I'm going to write, and this is the pattern, and you just kind of have to learn the pattern. So M naught like that. Well, let me write that in white. That's ugly. Let's see, where's here we go. So M around 0.0 equals. So the red bit is going to be, we're going to go like this, and then we're going to subtract like that. Okay, so I'm going to do plus, and I'm going to put parentheses. Negative 0.8 meters times 0. Okay, okay, minus, well, I guess you can do this in either order, 0 times 86.933 newtons. Okay, notice, okay, we've got a bunch of zeros there. Okay, all right, next, we're gonna cover J kind of. So that leaves a 2x2 matrix that looks like this. Okay, so we're basically doing the columns that are not in the J. Okay, and so again, we're kind of going to do a cross product as if the other things don't exist. Okay, so we're going to pretend they don't exist. This is called Cramer's rule. Okay, but the difference is when you do the J, when you do the one in the middle of the three, you need a negative sign in front of it. So that's the one tricky thing about this. Okay, and so that negative sign, so I'm going to go, I'm going to do a cross again. So I'm going to go down like this, 0.6 meters, and that's going to be times 0. Okay, and then I'm going to go back this way, which is 0 times negative 23.294 newtons. Okay, so note that in this case, oh wait, sorry, I did forget something. This is the J. This one that I did up here, this was the I. Okay, and the last one is going to be the K, obviously. But notice that so far, all of these things are coming out to 0. Okay, and then I'll do the last one, and I'll pick another color. Maybe I'll do blue in this case. And what we'll do is we'll kind of like highlight the K. Okay, and that basically means that what is left over once I kind of highlight that column is I'm looking at this right here. Okay, so I'm going to end up with a K right here. Okay, I'm going to get a plus right here. And that K vector looks like it's going to be kind of the interesting one. So if I go down here, I've got 0.6 meters times 86.933 newtons. Okay, minus, and I'm going to go back this way. Okay, I'm going to put another set of parentheses here, negative 0.8 meters times negative 23.294 newtons. Okay, it got a little small there. Okay, and so that is how we get the moment. Okay, so I'm going to do this on the calculator, noting that the I goes away, the J goes away, and that has to happen, right? Because there's no way for these forces which are in the X, Y plane, so this is X, and this is Y. Okay, there's no way for forces in that plane to cause things to rotate around the X axis or the Y axis. They can only cause things that rotate around the Z axis. So this K was the only possibility. Okay, so I'm going to plug these into the calculator, and I'll just write out the answer. All right, M0, so that's the moment caused by that force, is 33.525. We should note the units here. I had meters times newtons, so this is a Newton meter. Okay, and you know, and by the way, moments and torques are the same idea. So you know, like in the English system, a lot of times we'll talk about foot-pounds. This is equivalent. This is a meter newton instead of a foot-pound. Although usually we do newtons, meters, and foot. Like the order is not the same, but that's not really important. Okay, so notice this is what we ended up with. Okay, 33.525 Newton meters, and again, like I always keep five significant digits. And it's got a positive sign. So that means that this thing is probably going, well, it better be going counterclockwise. So it better be going this way, okay, because it's positive. Okay, so if we go back up to our original drawing, and we look at where I drew, and you're kind of like, well, which way is it going? Which way is it going to drive this thing? And it's kind of hard to tell. And the way we tell really is by looking at, or at least the way I tell, is I follow the line of action of the force. Okay, so I'm going to zoom all the way in. I'm going to follow the line of action. So here's our force right here. Okay, and it looked pretty, and now it looks less pretty. But I'm going to follow its line of action until it's somewhere where it's obvious to me what it's going to do, which way it's going to cause things to spin around this point, you know, that we care about. So in this case, if I put the force here, I think it should be obvious at that point that it's going to create a positive moment. That's going to be counterclockwise. Okay, so that gives me some faith in what we've just done. Okay? So that's the first way to solve this. Now, there's some really nice things about this matrix method. So I want to go in and I'm going to kind of write them down right here. Method one, I'm gonna kind of write the positives, and you can already see some of the negatives. Like there are, and I kind of just did this on the calculator when you weren't looking, but there are a lot of signs on this. Okay, if you look down in here, there's a lot of positives and negatives, and especially if you're going in 3D or blah blah blah, like you can imagine that this could get fairly complicated. Okay, and the signs, there's just a lot of places for sign errors. That's the number one problem with this. So usually in 2D, I'm not really going to use this. In 3D, I'm going to use it. It has a major advantage though. And the major advantage is that it takes care of the sign for you. Okay, so the sign is taken care of. Okay, and it's just going to like pop out. As long as you have defined everything correctly, the sign will pop out. Okay, and so that's the major advantage to doing it this way. Okay, so advantages, disadvantages are going to be... Okay, so I'll define those as the advantage is that the sign is done for you, and the disadvantage is that there's the possibility for a lot of errors. Okay, I'm mostly going to recommend that you can do this if you're comfortable with it anytime you want. I guess also error prone. It's also could be time consuming. Is in 3D, this is the recommended way to do it. Okay, because finding all of these things in 2D can be very, very problematic. Okay, so let's solve this problem again, but let's do it using method 2. Okay, and I guess I'll go ahead and put advantages and disadvantages. Okay, one, obviously the sign is not going to be taken care of for you. So let's see. I'll pause while I figure this out. All right, so obviously I erased a whole bunch of stuff, and hopefully you can see this is the same problem. And we're going to solve it with that second method, which looks something like this. And, really, I think probably we can get rid of those magnitude signs. But here's the thing. We're going to have to, think about this and make sure that we get the signs right. Okay? And the way that I've kind of done it is kind of like to do it like this with magnitude signs. And I think... I'm not really sure what the right notation is for this. I think usually what you see something like this equals FD, and it doesn't normally have that perpendicular sign on it, but I like the perpendicular sign. It reminds me that this distance is a perpendicular distance, okay? So it's similar to the direction vector, but it's a little bit different, okay? So let's consider this 90 Newton force, and I want to consider perpendicular distances to the 2.0, okay, which unfortunately I've accidentally deleted the 0. So let's put a 0 back in there. So here's a 0. Okay, so here's what's going on. I'm going to split this 90 into two forces. Okay, one is going to go this way. Okay, like that. And the other one is going to go this way. Okay, these are just like the forces I did last time. Okay, in fact, they're the exact same forces. Now, normally we do those and we would kind of add one this way. Okay, but I'm not going to add it that way, or I'm not going to add it this way, right? I'm going to keep them along the axes because I want to note that all of these forces are acting in the same point, and that's this point right here. Okay, so the portion of this 90 newtons that's going in the x direction and the portion that's going in the y direction are both going through that big dot right here. Okay, so then what I'm going to do is I'm going to find what those components are. So if we've done our trig correctly, okay, this one right here will be 90 times the cosine of 15 degrees, okay, because theta in this case is 15. And this one right here, they don't really have a lot of space for it, but it was going to be 90 times the sine of 15 degrees. Okay, it could also be the cosine of 75 if you prefer. Okay, so those are my force. So I've split it up into two forces. And the reason that I'm splitting it up into two forces is because this D that I'm going to be using has to be perpendicular to the forces. So what I'm going to do is I'm going to move this force, this one right here, I'm going to move it following its line of action until it's like right here. Okay, so So using a calculator, that's 86.933 newtons. Okay, and now it's got a distance, which is going to go from, well, let me use a different, color we can see. So it's going to go from, the point O, and it's going to go this way. Okay, so notice that the distance is perpendicular to the force. So this is D, okay, and this is the force. Okay, so that's one force. Okay, now the other force is we're going to do the same thing, but I'm going to move it until, so if we just kind of like slide it along its line of action until it's got a perpendicular location. So if I'm going to go right here, okay, and I'm going to get a force here of 23.294 newtons. And again, now it needs a distance from which we are trying to, we're trying to get the moment around this point 0. Okay, and so we're going to go down here, and that distance is the perpendicular distance for this force. Okay, so I mean, this is a little bit complicated, but it's not that, to me, it's less complicated than the other way. Okay, so in this case, m dot 0 equals, let's look at this vertical force, so 86.933 newtons. Okay, and what is the length of that distance vector? Well, it's 0.6 meters. It's given in the problem. Okay, now we have to think about the sign on that. Okay, and this is where the sign becomes difficult. All right, so in this case, I think if you look at that, you should be able to see that it is going to cause things to go counterclockwise. So this is going to get a positive sign. Okay, now the other force, okay, which is 23, so is going to, let's just do the force first. 23.294 newtons. Okay, and its distance is 0.8 meters. Okay, now it has a sign as well, and in this case, if we think about it, it's going to cause this thing to go clockwise. So that gets a negative sign. Okay, so it has a bigger moment arm than the other force, but it's a smaller force. So we'll see which one wins out. Okay, and if we plug that into our calculator, okay, we get an answer of positive 33.525 newtons times meters. Okay, which is exactly, I assume, so if we zoom out, I think we're going to find that that's exactly what we got earlier. And it is, okay? It's the exact same thing, okay? I recommend, so actually, if you look into your calculations of this one right here, you'll see that this is the exact same calculation, same calc, okay? So anyway, we get the exact same number to 5 significant digits, and in fact, in this case, to 6 significant digits, and that's all the digits that even showed up on the calculator. So, because it's the exact same math. And so to me, that is the easiest way in 2D. So I recommend this one. This is, I call it 2, but I'm going to call it your 2D way to do it. And the disadvantage really is that you have to think about the signs. Okay, you have to think about the signs and apply them. Okay, so that's what we did. When I was thinking about this sign, I had to figure it out which way it was going to be. I don't think that that's a huge disadvantage. Okay, the advantage to me is that it's calculation-wise, it's fewer calculations, fewer calcs, fewer places to make an error, et cetera, et cetera, et cetera. Okay, so that's kind of how that's really the way that I would recommend that we find moments in 2D. Okay, this last method, the last method is going to be, for this particular problem, challenging. Maybe we won't do it for this last method. Okay, I'll describe it for this last method. I don't really want to do it. So I'll give you an idea, and this is how I would do it for this last method. Okay, so I'm going to zoom in, and I'm just going to kind of show you what you would do. Well, come on, zoom in, punk. All right, punk. All right, so we would need to find the sine of the angle, the sine of this angle between R and F. Okay, and the reason that we want to do this is, and I like this method only because the only thing I like about this method is that it has an element of intuition. I always like everything that's got intuition. So this is R, if you remember correctly. Okay, so this is R. And it looks like that, okay? And R always starts at the thing we're taking the moment around, That's the tail, and then the tip is over by, where, somewhere on the line of that force. Okay, and you'll note that there's an angle between those two things. So the angle is right here, which I'll call that angle alpha. So maybe right here I'll do an alpha because we already have a theta on the drawing. Okay, and so we're kind of stuck with like, well, how do we get at that angle? First of all, that's a huge pain in the butt. But really what we're doing here, and what I want to do is I want to describe what we're doing, is this. So if I'm basically splitting this force, I'm going to do that force in, let's say, blue. Okay, so here's my force right here. Okay, and I want to split it into two components. One of those components is going in this direction, okay? And the portion of the component that is going in that direction has no moment because it's going right through the hinge. So you imagine my brother trying to break into the door, and if he's pushing right at the hinge, he's not going to do any, like, it doesn't matter. Like, that portion of his force isn't doing anything. The only portion that's doing anything is this portion right here. Okay, is that, it's kind of hard to draw that. If I zoom way in, it's this, it's this portion right here. Okay, so we draw a little right triangle. Okay, and I note that really this force is not acting out here. Okay, it's acting over here. Okay, so if I draw it right here, and noting based on that triangle that the size of that is going to be F times the sine, or it's really going to be the magnitude of F times the sine of that angle alpha. Okay, so if it's right here, if it's acting right here, okay, then its perpendicular distance is r, going all the way up there. And there you have it. That's the moment. Okay? So when do I recommend that? Well, first of all I want you to understand is that's where this sign comes from for these cross products. It's just trig. Okay? SOHCAHTOA is like the most powerful thing in all of engineering. If you're bad at SOHCAHTOA, if you haven't figured it out already, it's time to figure it out. Okay, time to work on it. Every time you see a triangle, write out SOHCAHTOA and start figuring out the sides, because that's like key and that's everything. Okay, so that's what we're doing here. Okay, so that's in a nutshell how we get a moment. And I don't really recommend ever using this F sine theta. There are times when that will be useful, and I'll kind of bring that up. But really, what we're doing is we're using this this kind of F times this one right here, the number 2. Okay, that's kind of the one that I most recommend using, especially in 2D. When we get to 3D, the cross product using the Cramer's rule, which unfortunately I deleted. It's kind of not really my policy. But that's kind of what I recommend. So anyway, so this is kind of a lot. I mean, it was a short lecture. We're only at 53 minutes, but it is kind of a lot of information. So I think what I want to do is I want to stop here, but I want to make note of what I want you to do in 2D on the homework. I'm going to try to give you problems that encourage you to do one or the other of these two methods in 2D. Okay, because it's going to be easier to do, for example, method 1, it's going to be easier in 2D, although, it's not always necessarily the best method. To me, method 2 is a little bit more intuitive. But what I want you to do is try to see if you can do it both ways. Or really, if you're stuck for time, do it the way that the problem recommends. I haven't looked at the problems yet, but I'm hoping that they have some that they recommend doing a certain way. If they don't, then I'll just assign one where I say do the R cross F, because I want to be able to check that work. But what I want to do is I want to make sure that you can do it in 2D, because when we get to 3D, it's going to be easier. It's going to be more. It's just going to be better if you can do both. So make sure you can do R cross F on a 2D. That way the 3Ds will work out. The nice thing about the 2Ds is everything's going to drop out except for the K term. The I's and the J's will disappear. So anyway, so that's moments in a nutshell. So again, I don't get to know any of you guys this semester, and that kind of makes me sad, and I'm lonely and everything, but I'll deal with it. But in the meantime, why aren't you guys coming to office hours? Come to office hours. I haven't had anybody come to office hours. Come to office hours. I sit in front of the computer for 8 hours a week, and there's nobody there. Okay, and while it makes me a little sad and lonely, it's totally fine as long as everything's making sense to you. But I cannot tell if things are making sense to you. So please come to office hours. All right, and beyond that, take care of yourselves, and I'll see you. So be easy. This is Dr. Wagner signing off, or Wayne if you prefer to call me that. Don't call me Mr. Wayne. That's annoying. All right, later, guys. Bye.